Okay, hello everyone. Oh, there is just a second. Oh no? You can enter it. So you can sit anywhere you want. So I actually have one audience. That's great. Pranav is here. Very good. So remember, I promised to do a tutorial on elliptic complexes. So this is index theory 6. So without much introduction, let's start. So let us recall. So recall elliptic complexes. So I said, imagine you have complex vector bundles E0, E1, En. So these are vector bundles over some manifold M. And imagine you have these differential operators Pi from C infinity of Ei. C infinity is always, of course, as you know, smooth sections of Ei to C infinity of I plus 1 for all I. Okay, so these are differential operators, as I said. They don't have to be the same order. I mean, they can be first order, second order, whatever you want. It's a very general concept, such that Pi plus 1 composed with Pi is equal to 0 for all I n. So what does it mean? Of course, it means that we have a kind of complex in the sense of homological algebra, right? So we have C infinity of E0, C infinity of E1, to C infinity of N. So we go to 0 and come from 0. So here you put P0 if you want, and P1. So it's a complex. Complex in the sense of homological algebra, as we know. So these are obviously infinite dimensional, huge vector spaces, complex vector spaces, but that doesn't matter. So, and the definition was that it's called elliptic. This is called an elliptic complex. I'm just recalling the definition we had from a previous lecture. If the symbol complex is exact, right? Symbol complex is exact. So what does that mean? So the symbol complex, so let me write it like this, i.e. for all x belonging to M and for all C belonging to T star M at X, this symbol complex just right here. The complex. So the symbol complex would be E0 fiber of E0 at X. By sigma, you go to fiber E1 at X. This one, En at X, go to 0 from 0, where sigma is equal to, so sigma is a collective notation for symbol of Pi at the point X in direction, cotangent direction. So I collectively denote them by sigma. That's kind of. Okay. If this the complex is exact. So of course, exact means its cohomology is 0. This is a chain, the co-chain complex, its cohomology should be 0. Every co-cycle should be a co-boundary and so on. Okay? So that's the definition that we had from we had last time. Now, as far as examples, of course, example 1 was elliptic operators. So elliptic differential operators are examples of such elliptic complexes simply because we can just take these two terms as a complex. So here we have C infinity of E0, and this is P, C infinity of E1. So the symbol complex for this to be exact just means that the symbol is invertible because there are two terms. Exact, if and only if symbol of this C is isomorphism or invertible. So whatever you do, you prove about elliptic complexes certainly hold for elliptic operators, but this is more general. So I also gave an example. I mentioned an example. I didn't prove it. Example of an elliptic complex. So let's go through that in some detail because, yeah. Any questions about this one? Any questions? Okay, good. So now, maybe I should switch to actually to maybe I should pin myself. Might be easier. I forgot how to pin myself. Do you know how to pin myself?
So there's 3 dots on your picture.
What's that?
So there's a picture with, there's a video of you there. If you just hover your cursor on it, you'll see like 3 dots.
Oh yeah, I just don't find that. That's my problem. Oh yeah. Yeah, pin video, right. Okay, maybe that's better. Okay, thank you. All right, so now let's look at the Rham complex. So this is going to be example 2. So the Rham complex is an elliptic complex. So let's see why. So the Rham complex, of course, is, remember my notation was like this. Differential is V. Well, of course, n is dimension of n. Okay, so what is the symbol complex in this case? Of course, symbol complex is, we have here base 0 of T star M 0 at X, say, base 0 T star, base 1, rather. Yes. at x, and then wedge 2 and x, and then we have hn T star and x go to 0. So we calculated the symbol of the de Rham differential, as you remember. It was essentially exterior multiplication by this cotangent vector c. There was an I, but the I doesn't matter, doesn't play a role in the arguments at all. So it was symbol of d at xc is equal to minus I c wedge. So that's exterior multiplication. So now the question is why exterior multiplication is an exact, defines an exact differential here. So we have to prove it, right? So why sigma is exact. Well, perhaps you may be able to prove directly by hand. If you get your hands dirty, maybe you can prove it. But I'm going to show you a kind of nice standard, of course, way to prove that, which is useful for other things as well. So there's a general idea at work here. It's good to pay attention to that. So, to put us in a kind of more general context, this is a purely linear algebra question, by the way. This is just a linear algebra question. So we have to go back to our linear algebra. So let's assume you have V, a finite dimensional vector space. And then you can define a kind of complex like this, wedge 0 of V, wedge 1 V, wedge 2 V, to wedge n V to 0. And we are going to, like here, fix a vector in V. Fix C in V. Then you can define, as in this case, an operator which I call it exterior multiplication still, so I denote it by XC, XC, XC. So this C is equal to C wedge. Still, same operation, exterior multiplication, right? Okay. So our goal is to show that if this C is not 0, then this complex is exact. So lemma is that C different from 0 implies that this complex star is an exact sequence. Okay. So how can we do that? So proof, maybe I just start here and then I continue. So for this, there's a standard way. You define a kind of interior multiplication associated to this C. And the interior multiplication plays the role of a homotopy operator for this exterior multiplication. And this is a standard. Anytime, most of the time, you want to prove something is exact, you construct a homotopy operator, and then you will see immediately why it's going to work. So let's start. So to start with, let us fix an element in V star. A linear form on V that the only condition on F I need is that F at C should be 1. That's all, or non-zero. Such that F at C is equal to 1. This always exists, of course. There are so many of this, right? So we can always do that. Then what we do? Then we are going to define operators in this direction. So let me just write here without even write more. So there is this, I define IXC, and so on. So define IXC in, so this IXC is decreasing the degree, right? So IXC is going to go from wedge P of B to wedge P minus 1 of B. So it's defined like this: IXC of V1 wedge, so on. So generators, or not generators, I mean some homogeneous element like V1 wedge Vp. Let's be equal to sum minus 1 to the power pi. You just apply f to the ith entry here and drop that entry. So f of vi, and then I just write v1 wedge, and then we have to delete that ith entry. This standard sign of deletion is hat. When you put a hat, typically, at least in differential geometry, linear algebra is deleting, and then we have HP. Okay. So this certainly is a well-defined operation. That's easy to see, and it decreases the degree. So it's going in from right places to right places. Now the thing is, it has this nice property that you can check. And that's most important property is that. So here I of course should go from 1 to P. You have a deletion of V1, V2, Vp, all of them. So there are P terms here, so I alternate. So then check that IXC composed with XC plus XC composed with IXC is equal to identity of wedge P for all P. So that's the, of course, if you prove this, then you're done, right? Then this immediately shows that this is a very standard argument. It happens all the time in homotopy theory and stuff like that, right? So anytime you have a relation like this, if you have something in the kernel of XC, this is killed by your differential, well, you apply this equation to that element. It shows that that element, because here is identity, that element is XC of something, is XC of interior multiplication. Right? So this is a very standard argument. So this implies, of course, that star is exact. That's the end of the question. Okay, so i.e. the Rham complex is exact, is elliptic. That's what we wanted to show. Right? Okay, so we dealt with symbol sequence. Okay, what else? Now, okay, so now there are two classical results about the Rham complex that we are going to generalize to elliptic complexes in general. So these two classical results, one of them is the Wrong Theorem, the other one is Hodge decomposition theorem. So we are going to I'm going to recall this thing just for refreshing these results, and then we point to the direction that when we prove this elliptic regularity finiteness, then we'll prove those results for elliptic complexes in general. Of course, I have to give more examples of elliptic complexes, hopefully today, but let me just recall these results.
So both del and del bar are also examples.
Yes, yes. So maybe, yes, so I will record that soon, right? So, so index of, so first of all, let me just, two results on the Rham complex. So this will be generalized soon to all elliptic complexes. So I just recall these results, but when I prove these results for elliptic complexes, these results also follow. The first result is the Wrong Theorem. The classic result. It just says that if your manifold, smooth manifold, of course, is compact, then these the Rham groups are finite dimensional. So if M is compact, the Rham cohomology group HP, the Rham of M, which is kernel of D to the image of D, of course, going from right places to right places. This is finite dimensional for all P. So that's one result. This is a standard result. So now then you can see how this is going to be generalized. So if you have an elliptic complex over a compact manifold, its cohomology is finite dimensional. So generalization is if E0, E0, E1, n minus 1, well, this should be from C infinity. So let me put it like this actually. For any elliptic complex over a compact manifold, the cohomologies groups H P of, now we have to put M and E, which is by definition kernel of, so maybe I put I, kernel of PI from C infinity of EI to C infinity of EI plus 1 divided by image of EI minus 1 from C infinity of EI minus 1 to C infinity of EI. These groups are finite dimensional for all R. Okay, so this we will prove soon, but this is the exact generalization of this. So these groups are finite dimensional. As a result, we can take its Euler characteristic. So we can define the so-called Euler characteristic of an elliptic complex. So you can define it in an obvious manner, right? So you just define Euler characteristic of M and this elliptic complex E is some -1 dimensional is HI and E, right? One from I from 0 up to maybe we assume is N, I guess. Yes. So this Euler characteristic as a result is well defined. Okay, so that's one thing. Now the question is Euler characteristic an index of an operator or not, right? So that's the question. And in fact, we will show that this Euler characteristic is index of a differential operator. To construct that differential operator and to prove that results, we need some more results. Well, let me mention here. And then we shall prove. This Euler characteristic of M and E is equal to index. So by index we mean threshold index. Let me just of a differential operator. Okay, so this will do. Because that's not obvious here, right? Because we have several teams and the elliptic complex is not an elliptic operator in any sense, right? So we have to cook up an elliptic operator in a natural way out of this elliptic complex. And then we have to prove that that's actually its threshold index is really Euler. So this is, to do this, we need actually the second step, which is the Hodge decomposition theorem. And for Hodge decomposition also, let me recall it in the classical original version. So the result, the second result, classic result, is Hodge decomposition theorem. So now for this, I have to assume that you don't have just a Riemannian, you don't have just a manifold. There should be a Riemannian metric, and I am assuming also there's an orientation. Okay, so let Mg, and of course it's compact again, be a compact Riemannian manifold. Okay, so compact. Just to be safe, I'm just assuming oriented, but I really don't know how much I need of this. But okay, so just to be safe, let me assume. So imagine you have the really important ingredient is that now we are going to include this Riemannian metric. In order to do the Hodge decomposition, you need the Riemannian metric. That's very much a Riemannian story. So be a compact Riemannian. So first of all, then you get the star operator. I will define these things soon. The star from omega, say I m to omega I minus 1 and for all I. So remember now this is, notice that this is decreasing the degree. So this star is the adjoint in appropriate sense of D. It satisfies the conditions that D star squared is equal to 0. And let this be equal to D plus D star squared. So of course, since D squared, D star squared of 0, so this is D star plus D star D, right? That's what we have. So this is called, I will define this precisely in detail with examples soon, but This is called Hodge Rham, maybe Beltrami. So Laplacian. So names of 4 great mathematicians is packed into this Laplacian. Okay. So for flat space, with standard orientation and standard Euclidean metric, this delta turns out to be equal to minus some d2 dxi squared. There's a minus sign. Okay, so anyhow, so we have this delta. So then this Laplacian. So then the Hodge composition says the following. So Hodge composition is this. So you can decompose the whole space of P forms as the direct sum, or orthogonal direct sums of 3 pieces. Okay. So so let me write here. So we can write omega P of M as image of D, direct sum image of D star, direct sum kernel of delta. So notice that this delta, of course, goes from omega Pm to omega Pm, right? So you go up and down, down and up, you add, you don't change the degree here, right? You don't change. Okay, so this kernel of delta from omega P to omega P, first of all, what is it? There is a notation for this. These are called harmonic P forms, okay? So another notation for this is harm P n. So these are called harmonic P forms. So okay, so what does this result says? I mean, the thing that you want to keep in mind is the mental picture is that there is really like a decomposition like this, image of D star. And here is just the space of harmonic forms. So this is like the Hodge room. This wall is image of D, this wall is image of D star. Here is harmonic P forms, orthogonal direct sum decomposition. And an easy corollary of this immediately is that actually there is a naturalized morphism between kernel of Laplacian and cohomology. So this is the thing. So let me write it. So a corollary of this Hodge decomposition is that the canonical map that sends an element here, omega, belonging to kernel of Laplacian, a harmonic P form to its class belonging to the heat Rham group. Is an isomorphism of vector spaces. Okay. In particular, this shows that this kernel of Laplacian is finite dimensional. If you believe in the Rham, but if you don't take the Rham, you want to start from this. This also implies the Rham because you can show that this Laplacian, its kernel is finite dimensional as a result of being elliptic. Okay. So here, kernel of Laplacian, of course, anything in the kernel, immediately we'll see soon that this is going to be in the kernel of D and also kernel of D star. So it's a closed P form and is also co-closed. So the map is defined, there's no problem. I mean, here is really just a subspace of forms. There is no quotient here, right? Here you have to divide, but here we don't. But the map is, when you go to quotient, it becomes an algebra. Okay, so this result also we will extend to all elliptic complexes. Okay, so that's a good thing to have in mind, that will extend to all elliptic complexes. Amazingly, all these results comes from one single result, which is elliptic regularity and finiteness theorem. So that's just a consequence of a general result that we prove that. All right, so this is now, so we are in a good position. Now I'm going to use this Hodge decomposition and Hodge theorem to show why Euler characteristic is index of an operator. So we will construct an operator, we'll see why Euler characteristic of a manifold is index of an operator. So that's going to be our first example, classical example of index theorem when we do everything at the end. So any questions or? No questions? Okay, so now I can move on. No. I thought there was a question. Okay, so now consider the following complex. Direct sum omega 2p of m over all p. You go to direct sum omega 2p plus 1 of m of p. So we just take all even forms and we want to go to odd forms. The operation that we are taking is d plus d star. Okay, so of course now this is one complex, and one vector space, and this is another vector space, and this is an operator. If we prove that these operators are fretful, then the index makes sense, and the claim now is this: index of d plus d star is equal to Euler characteristic of
You mean from some suitable compilations of those two questions?
That could be, but I don't need that. I will prove that even without completion, if you look at just this C infinity forms as a vector space, indeed algebraically is also fretful in the sense of my first lecture. So you can complete, you can do L2 theory. Of course, L2 is not enough. You have to go to subroof, because when you go to the target, you have to put subroof norm. It's inevitable. These operators, differential operators, are never ever bounded in L2 norms. You have to construct it. Anyhow, so but we'll prove that this is fretful, and that's in the algebraic sense also. So that's what we are. So let's prove this. So, so what is, for example, what is kernel of this operator? Going from there to there. What is kernel of d plus d star? So kernel is going to be a sequence of forms like this: omega 0, omega 2, omega 4, so on. That's killed by d plus d star, right? So if you apply d plus d star to this, omega 0, omega 2. We get 0. This is, of course, if I know leaf, you have these equations now. D omega 0 plus D star omega 2. This is a one form that has to be 0. And then we have D omega 2 plus D star omega 4 has to be 0. D omega 4 plus D star omega 6 has to be 0, etc. Just now you apply this star to this and D to this equation. Right? So apply this star to this and D to this and add them. Then what do you get? Because the star squared is 0 and D squared is also 0, we get what? Then is apply this star to this. Oh no, I'm going to apply, so let's apply D to this, sorry. And D star to this. Then what do you get? Then we are going to get, well, D squared is 0, get D star omega 2 plus D star D omega 2, which is Laplacian of omega 2 is equal to 0. And similarly, you can show that Laplacian of omega 4 is equal to 0, and so on. Now, what about omega 0? Well, omega 0 is very easy. You can just apply this star to the first one, and then you get this star D of omega 0 is also equal to 0. But this is exactly also Laplacian on functions, because omega 0 is a function. So you just go up, down, but if you go down, you get 0. So the Laplacian on functions has only one component. This is like kernel divergence of grad or something like that, business. Anyhow, so what do you get? You notice that, okay, all these guys are harmonic, right? In order to be in the kernel of P plus D star, all forms are harmonic. And by Hodge theory, by Hodge decomposition, we know that dimension of the space of harmonic forms is exactly dimension of cohomology. Right? It's actually isomorphic to cohomology. So from here, we get that dimension. So first of all, let's get maybe more precise information. We get that kernel of D plus D star. Now, as it goes from even to odd, okay, so that's equal to direct sum of harmonic 2p, okay, over all p. And also, in a similar way, you can also show that co-kernel of D plus D star, which is going to be equal to kernel of D plus D star, but this time going from omega odd to omega even. Okay. But if you adjoint this, you're going to get same operator, but different spaces. So that's important. From omega odd to omega even. For me, omega odd is direct sums of all omegas and so on, right? So that's also equal to direct sum of harmonic 2p plus 1 forms. That's it. Okay, so now you can see what the index is. So the index then is just dimensions of those subspaces. I mean, those spaces, just sums of dimensions, right? So it follows that index of D plus D star is equal to sums of beta to P, maybe I put B to P, minus sums of B to P plus 1, which is sums of minus 1 to the T EP over P. I'm just using a different notation called petty numbers. These are dimensions of cohomology groups, the Rham groups or whatever. There's also the Rham isomorphism, right? So that's, they're all the same. So that's equal to Euler characteristic of M. So this is the dimension of HP the Rham of M, which is the P petty number. Another notation, as I said, P petty number. Okay, so that's very nice because it just we just showed that the Euler index of this elliptic complex, which is the Rham complex, is really Euler characteristic of classical Euler characteristic. So, in other words, we showed that the classical Euler characteristic is index of an operator. So that's equal to chi. Well, just okay. So we are going through this example in this tutorial or similar examples in order just to gain some insight into general results. So that's the purpose of the tutorial. Any questions or comments? All right. So I think okay, so now
How does the symbol for D star look like?
sorry?
How does the symbol for D star?
Symbol of the star. So symbol of this star, we will compute actually the adjoint of exterior multiplication in terms of Hodge star operator, and we will see it soon actually. But I have to spend a little bit of time again on linear algebra, developing this Hodge star precisely, and then we'll see the symbol comes out very easy. Yeah, that's okay. So now. There is a result that relates Euler characteristic to, well, this is the result that relates Euler characteristic to actually index of an operator. But there is a kind of index theorem here that was discovered before index theorem of Atiyah-Singer, and that's a kind of prototype of index theorem. So I recall that result. And I will tell you what it says now. Okay, so this is the Gauss-Bonnet theorem. It's a classical result of differential geometry. So what does this result say? I mean, the setting is exactly what we have over there. So assume be oriented. Riemannian. Closed. Manifold. Closed means as compact without bound. Closed manifold of even dimension. UN. Then, so this is what Gauss-Bonnet says. Then index of, then Euler characteristic of M is equal to, I believe it's going to be something like this: 1 over 2 pi to the power n, maybe. I'm not 100% sure. Okay, integral over M of a certain form, differential 2 and 4, This differential 2 and 4 is Pfaffian of omega. So that's the result. So let me explain what is this omega, for example. Maybe I put R here because this omega, I'm using too many omegas here. So I had omegas before, so this is R. So R is, so it's an skew symmetric matrix, I mean 2n by 2n matrix of two forms. So if you like, R is a huge 2n by 2n matrix of two forms, which is skew symmetric. So on the diagonal is 0 and is a skew symmetric. And Pfaffian is essentially an invariant polynomial, which is the square root of the determinant that exists on these skew symmetric matrices only. Pfaffian is equal to square root of, so I just write it like this, but be careful about the meaning of this. Square root of the determinant on skew symmetric matrices. So if you apply this polynomial function on this matrix of 2n forms, you're going to get, matrix of 2 forms, because the polynomial is of degree n. Determinant has degree 2n, right? Square root has degree n. Apply this to this matrix of 2 forms, you're going to get a 2n form. Right? So we're going to 2n form and integrate that 2n form, and that's the result. Now, let's kind of unpack this, see what it says, at least in dimension 2 and dimension 4. And then we'll see what it entails and what it's saying.
And it's just a convention.
Sorry?
R is just a convention.
R is what?
Convention.
R is curvature matrix, yes, sorry. Yeah, exactly. So I should, R is curvature matrix. Curvature has many incarnations, many different versions you can write curvature. One is like a matrix of 2 forms. It's a matrix value 2 form. That's what curvature is, right? Okay, so we will I think we'll get to that. We have to get to that. Now let me just write down this result in the special cases of dimension 2 and 4. In dimension 2 is a very classic result. So with G handles, chi of n is 2 minus 2G. So remember, n is not just a smooth manifold. There is also Romanian Method. So the result in this case says that chi of n is equal to 1 over 2 pi integral Gauss curvature as a scalar function. It's a scalar function on the manifold multiplied by this 2 form, volume 2 form, you get a 2 form, and integrated over n. Okay. So that's the result in this case. Simplifies in this case. So Gauss curvature is is half of scalar curvature. Yeah. K is equal to half of scalar curvature. Just if you wonder, in case. So this result is a 19th century result. This was known. The local version was done by Gauss himself, and Bonnet did some generalization, again local, and then someone in Germany, I forgot his name, I think around 1860s, 1870s, noticed that you can piece together these local results and prove this result, which is. Now, if you think about it, this is an amazing result, right? You think about it, this is an incredible result. Why? Why is it an incredible result?
The left-hand side is different.
Exactly. Left-hand side is purely topological, has nothing to do with metric. It's a completely topological object. You can just change the manifold in any way, as long as you're not doing any drastic things, you're not changing topology, it's going to be the same number. But the right-hand side, it looks like at this k, point to point, highly depends on choice of metric. But when you integrate over the whole, these up and downs, changes, cancel each other, and you always get same number. And of course, another amazing thing is that this number is also an integer. Minus 2 is an integer, so that's another surprise. But the biggest surprise is that this is actually independent of g. All right, so that's a very, very powerful result, beautiful result. Now let me write down the 4-dimensional case. So to reach, I should tell you, to reach from here, 2-dimensional to 2n-dimensional case, it took maybe 40, 50 years just to guess what the formula is and to write down. And then another 20, 30 years, maybe 20 years, I would say, to give the most kind of elegant proof that was done by Chern. But before that, there was, so there's a beautiful story. You start from this local Gauss-Bonnet to here. So this is just a beautiful story that should be told another time.
I mean, it's true for all dimensions. It's just that in odd dimensions, the path is also 0.
Yeah, it's true for all dimensions exactly. Euler characteristic is 0, yeah. And that's also 0. So you get 0 equal to 0. So it's not as much content, but it's interesting maybe. So dimension. So this is dimension 2. So that's with it. So let's go to dimension 4. So again, we have this mg. So the result in this case says that chi of m. Of course, there is no genus in 4 dimensions. 4-dimensional objects are much more complicated, right? So it's not genus formula like this, but we have that alternating sum formula, that Poincaré definition of Euler characteristic, alternating sums of petty numbers. So that's the thing, right? So now, in this case, the result, I believe, says that this is one. You can check Wikipedia or somewhere. 32 pi squared integral over n. So it's going to be so Riemann curvature tensor squared. So you get a scalar. So this is the full curvature tensor. Take its norm in appropriate metric which exists, and then in between you have Ricci. Again, you have to compute its norm. And then we have scalar curvature, SC. Now, and then times the volume 4, which we need anyhow to get a form. So I have to, so of course there is a square here. So not to tell you a lie, I have to check my notes. So the formula in this case is, let's see, what's the formula in this case? Okay. Oh, 32 pi squared is correct. Riemann squared minus 4 times Ricci, first of all. And then plus this square. Yeah, otherwise we'll come. So this is not easy to come up with this term. It took a lot of effort. Again, it's an amazing story, but we have to do it another time, hopefully. So this is the thing. So now you can imagine that to compute the general form, 2n form, is going to be much more complicated. All things that enter into this curvature tensor R is going to play a role. I mean, there is a closed formula for Pfaffian, of course. We can write it as omega 2i's, but yeah, I mean. So all three curvature tensors appear here: Riemann, Ricci, scalar. There are three of them. All three appear already in dimension 4. So that's okay. So this is now an example of an index theorem. So one of the things that you're going to see is that a single index theorem generalizes this. So it implies Gauss-Bonnet theorem. So that's one of the things that one should see. Once you learn index theory, you have enough facility. You have to be able to derive this result from a TSE. This can be done. And this was one of the first examples of index theorem that kind of was convincing that such a general theorem should exist. So this is as far as Gauss-Bonnet goes for now. Maybe take a 2 minutes break or something, and then we maybe if you have questions, we can discuss, and then I'll go through other examples. So far, okay. So we saw that the Rham complex is an elliptic complex. I wrote down the general things that we are going to prove for elliptic complexes, the generalizations of Hodge decomposition and Wrong theorems. And one example of like a single index theorem. So if you don't have any questions, maybe I can just continue. Just should I continue then? Okay, maybe. Okay. So Euler characteristic is of course very important invariant for manifolds. I mean, this is a topological invariant. You can define it for any space as long as these cohomology groups are finite dimensional, right? And there are finite many non-zero ones, so you can define it. There is another invariant that also is very important. That's called signature of the manifold. It's already you. So signature. So now, assume that you have a, so the assumption is this: M is a closed, oriented manifold of dimension 4K. So its dimension should be at least 4, 8, 12, so on. It should be a multiple of 4. And it should be oriented and closed. Then you have this intersection pairing. Right? So you have this pairing H2K M. Actually, this is purely topological and integral story to start with. So you can take pairings over Z. So cross H2K Z to Z. It works like this. So it's an intersection pairing. So if you have a class here, alpha and beta, you can send it to alpha cup beta. So you're going to get a 4K class, cohomology class, and then you integrate it or you evaluate it on the fundamental cycle of the manifold, which is of dimension 4K because it's oriented. So you compute it over. So this is the fundamental class. Okay, so because of this dimension 2K here, I mean, this is a symmetric integral bilinear form. Okay, so this defines a symmetric bilinear form. So symmetric bilinear forms are the same as quadratic forms. Quadratic form. On H to K and Z. So there is an alternative way of working with this, which perhaps maybe it's easier to grasp if you don't know enough of these things. I mean, so this is, if M is a smooth, for example, there is a de Rham incarnation of this, right? So if M is a smooth, you can just take this map from de Rham cohomology, middle de Rham cohomology of M, which is a vector space over R right now. So to this one, to R. So again, so this form, 2K form, class alpha and beta, you send it to integral alpha h beta over M. Remember, this is a 2K form, it's a 2K form, it's Beige, it's 4K form, and you integrate over the manifold. You have an orientation, so you can integrate. So this is a de Rham incarnation of this. Of course, this is much more powerful because you go over Z here. Here, we have kind of washed up some information, a lot of information by working over R. Now, this form is non-degenerate, first of all. So Poincare duality shows that this is a non-degenerate form. So we have this quadratic form, symmetric non-degenerate form on this cohomology, middle cohomology space. So as far as linear algebra goes, the only invariant that this form has is its index, which is number of positive eigenvalues minus number of negative eigenvalues. It's not quite correct to talk about eigenvalues because a symmetric form doesn't have an eigenvalue. But what I mean is that when you go to standard basis to diagonalize, you have so many positive and so many negatives, and that's fixed. That doesn't change. This is called law of inertia or something in linear algebra. Maybe Sylvester's, I think it's called Sylvester's law of inertia or something, right? You can always diagonalize such quadratic forms, but the number of ones and number of minus ones is always the same, no matter which basis to choose to diagonalize. So that leads to the following definition. So the signature, so I didn't give a notation for this form, so definition then. The signature of M for K is the signature of this non-degenerate form. So maybe, I'm not sure, maybe I should put sigma of m, signature, by definition is number of positive minus number of negatives. So you see, the sum of the two is always 2k because the form is non-degenerate. There are no zeros on the diagonal, right? So you can, Silvester's theorem says that you can always, in basic linear algebra now, really, says that we can always write this form as 1, 1, 1 minus 1, 1. Okay, so we just take the difference. This is called signature from linear algebra. This is an important invariant for quadratic forms like that. So this is called the signature of the manifold. Okay. So this signature, historically, I believe, was defined by Hermann Weyl. This is due to Weyl. Could be 1920s. Probably this is correct, but please check for yourself. Anyhow, it's a topological invariant, right? It's a purely topological invariant because, sure, I used the wrong cohomology to define it, but we had another definition just using cohomology over Z, and you can tensor with R to get real cohomology groups, and then you have this intersection form too. Okay, good. So now let's look at some examples of this signature. So the question is, what is signature of S4, for example? The simplest oriented closed four manifolds you can think of, I can think of, the first one is S4 anyhow. So what is signature of S4? Can you guess? Sorry? It's 0. Why?
Oh, I need H2.
H2 is 0. It's 0 for a kind of obvious reason because H2 is 0 to start with. This is equal to 0 since H2 S2 S4, sorry, is equal to 0. This we know. Right? Okay. It's also 0 for another reason, which is a much deeper reason. So let me mention this second reason, which is due to Tom. So René Tom showed that I believe this was 1954. He showed that the signature is actually a cobordism invariant. Is a cobordism. What does that mean? It means that if M1 and M2 are boundaries of some manifold of higher dimension, if M1 union M2 is equal to boundary of some n, if such a thing is true, then signature of M1 is the same as signature of M2. So notice that this is far more stronger than homotopy invariance. Homotopy invariance just means that if you have a cylinder, you perturb this from one end to another, then they are the same. But here is for any manifold, if you can traverse M1 along some n plus 1 to 4, k plus 1 dimensional manifold, reach to M2, you're going to be the same. So this is a very, very deep result of Benetton. So in particular, if your manifold is boundary of another manifold totally, then its signature has to be 0 because it's coordinate to 0 manifold, empty manifold. So the corollary, in a sense, is that if n is equal to boundary of n, then signature of n is equal to 0. So that's another example. So of course, it follows that S4, signature of S4 is equal to 0 because S4 is the boundary of the ball, right? So hence signature of S4 equal to 0 because S4 is boundary of this 4-dimensional ball, which is manifold of dimension n plus 1 with boundary. So that's one case. Now, there is a fun case to do, again by hand this time. That is the signature of, just for fun, compute signature of T4. So what is this T4? So T4, of course, we know is S1 cross S1 cross S1 cross S1. So 4 copies of circles multiply, you get S4, you get T4, the 4 torus. It's a closed-oriented manifold, and the question is, what is its signature? So you can approach this result in different ways. I suggest you look at it just directly by brute force computation. So first of all, you can write down a basis for middle cohomology. Do all the computations. So first of all, what is H2 Rham of T4? Sorry?
We can use Collet.
Sorry?
I mean, we can use Collet formula. And
yeah.
The product of H2 of T2 tensor H0 of T2, direct sum H0 T2, and then direct sum H1 T2 tensor H1 T2.
Yeah.
So that will be R direct sum R, direct sum I direct sum R, so rank 4.
Its dimension is going to be 6.
Yeah.
So is 4 choose 2. 4 choose 2 is 6, right?
Yeah.
So let me write a basis for this thing. Basis. 4 2. So this manifold is flat, right? So you can write a basis for all differential forms. So you choose coordinates, global periodic coordinates x1, x2, x3, x4, right? And so then you take dx1, wedge dx2, dx1, wedge dx3, and then dx1, wedge dx4. And then you take dx2, wedge dx3. And then you take dx2, wedge dx4. And then you take dx3, wedge dx4.
No, I realized my mistake. So even in the Collet formula.
Yeah, right. Good. So this is 3, 2, 1, 6. So this is a basis. And in fact, you can write down everything as constant cohomologies, as constant linear combinations of such things. Because this is 6-dimensional space, and this is a basis for this space. Then what you can do, which is kind of fun, a little fun, is to just compute these. So imagine, let's call this, for example, alpha 1, 2, call this alpha 1, 3, etc. These two forms, and compute the intersection number of these two forms, because we have to know how this intersection pairing works on this thing. So for example, just check what is alpha 1, 2 wedge. Or maybe I just use this. Yeah, let's call it wedge alpha 1, 3. It's 0, right? So let's compute alpha 1, 2. The only thing that contains alpha 1, 2 and is non-zero is alpha 3, 4. Wedge alpha 3, 4. This is going to be dx1, wedge dx2, wedge dx3, wedge dx4, right? So now if you integrate this, you're going to integrate this, and with respect to some natural, this volume form, integration is 1. So just okay, so the value of this, the product, this writing the form here, so alpha 1, 2, alpha 3, 1, anyhow, is equal to 1. So you can similarly compute. You're going to get 3 plus 1 and 3 minus 1. You will get, so for example, let me just write down alpha 2, 3 wedge, alpha 1, 4. What is that? Well, this is dx2, dx3, let me not put wedge, dx3, dx1, dx4. Now this moves over this twice, so it gives me dx1, dx2, dx3, dx4, right? So you get a plus sign, and again, you get 1 here. But sometimes you have to switch odd number of times, and you get minus 1. So if you write it, you get 3 plus 1 and 3 minus 1. So the question is, what is the index of this quadratic form? Because in the index means that you have to find a basis over which some of these guys are plus 1 with itself. Intersection pairing with itself is plus 1. Intersection pairing. So these ones, intersection pairing with itself, this one is 0. Because dx alpha 1 to wedge alpha 1 to is going to be 0, right? So that's not the basis. That's not the basis that diagonalizes your form. You have to choose another basis. It's kind of a little fun to do that. So if you do that, you're going to get 0. You see that there are, so you get 0. But this 3 plus 1, 3 minus 1 is interesting because it will come in a different way soon. Because these forms, dx1, dx2, for example, it's a harmonic form on this space. So yeah, we'll see that. Anyhow, so another example, which is kind of fun to look at, is signature of P2C, complex projective plane. I believe this is equal to 1. Of course, signature of S4K, again, is 0 for all K equal to 1 to so on, because the middle cohomology is 0, so that's not interesting. But there are many cases where this is non-zero and is. So this is an interesting topological invariant, and it's more subtle than Euler characteristic, and it was discovered long after Euler characteristic was discovered. Right? So it was kind of hidden behind the surface. Euler characteristic, at least for surfaces, was discovered by Euler, and to some extent it was discovered by Descartes in the 1600s. So, but this is 1910. Okay, so now, but the question is, we saw that Euler characteristic is index of an operator. The question is this an index of an operator as well? Okay. So that's the question. Is a signature index of a differential operator. So the answer is that yes, it is the index of a differential operator. Yes, it is. And in fact, there is a differential operator which looks very similar to the operator that we used for Euler, except that the domain and target spaces are different. So, so this is a theorem, a proposition, really, because it's proved just using. Well, we have to use Hodge theory as we did for in the case of Euler characteristic, of course, and a little bit of algebra. But let me write it. Proposition is that sigma of m is equal to an index of d plus d star. So I'm going from omega plus to omega minus. So the question is, what is omega plus and what is omega minus? Well, let me define it like this. So omega plus m, it's this plus one eigenspace of the operator gamma. So I'm going to define an operator gamma that goes from this space omega. This is very important to use complex valued forms. Omega. So this is really direct sums of all forms now, right? Complex valued E, P bigger than or equal to 0 of n. So I just denoted by omega, but omega c, that's this notation we used before. So to itself, so this operator gamma, I guess this is called chirality operator or something like that, but it doesn't matter. It's essentially, gamma is going to be depending on what is the dimension of the manifold and what is the space that is acting on. Let me just write in a kind of very rough way now. I will make it precise. It's plus minus star. It's going to be Hodge star operator, plus minus. And there is some I here maybe also. It doesn't matter for now. The thing is that this gamma squared is equal to 1. Always, always, on all degrees. Okay. So gamma, if you want, goes from omega c p to omega n minus p. That's the like in the Hodge star operator. The issue is really signs. You have to pick signs in the right way, multiply in the right way, such that you always get gamma squared is equal to 1. Okay. So this is a 4K dimensional manifold. Let me maybe emphasize here. So once we define this precisely, we're going to see using Hodge theory that indeed that's the case. So gamma restricted to omega plus is equal to identity of omega plus, because gamma squared is 1, so there are two eigenvalues, 1 and minus 1. There's one eigenspace, and the other one, restricted omega minus is equal to minus 7.
Why did you have to complex it?
Sorry?
Why did you have to complex it?
Oh, because star squared is never 1.
Right, it's a minus 1 to the n minus 3.
Yeah. Yeah, you can never fix it without multiplying by complex numbers. So that's a very important point. I'm going to write it soon. Once I define this Hodge star. Okay. Just like this. Okay, so if you believe in this proposition, then this is indeed index of this elliptic operator. T plus this star, this we can call it signature operator if you want. But going from some special space of forms to another space of forms, the exons of this thing. So that's so
but the right hand side, that definition won't it make sense for any dimensional manifold?
yeah, but this statement, the way that it works, it just makes sense only. It's true only for k dimensions. Yeah, this decomposition is important, right? So so now the question is, okay, so you can apply index theorem to this, and what kind of result you get in this case? In fact, this case was also done already before ATS Singer. This is Hirzebruch signature. So let me write it down. So the index theorem in this case for signature theorem, for signature complex on operator, gives Hirzebruch signature theorem, which already exists. Like Gauss-Bonnet theorem that already existed. So Euler gives you the kind of expression for Euler characteristic. So signature theorem of Hirzebruch also gives you an expression in terms of integral of some differential forms for signature operator. Okay. So Hirzebruch signature theorem. So what is this result? This result, so let me start from dimension 4. Then Hirzebruch's theorem. So this was done by Hirzebruch, by the way, in 1954. You notice that Tom's result also I mentioned was done in 1954. This is not accidental. Hirzebruch used Tom's result in order to prove the signature theorem before index theorem. So dimension of m is equal to 4, then signature of m is Hirzebruch said is equal to integral over m 1/3 of P1. But P1 is the first Pontryagin class of tangent bundle. This is the first Pontryagin class. Okay, so that's this result in this case. Okay, so we'll recall the definition of Pontryagin classes, term classes, and term character. This is unique for different formulations. And in general, what Hirzebruch showed that there exists actually an expression. In general, Hirzebruch showed that there exists an expression sigma n is equal to integral over m for 4k dimensions, L of E1, E2, so on. So this is dimension 8, this is dimension 4, this is dimension 8, 4 in dimension 8, and so on. So this is a polynomial in these variables. You multiply them, add them, you get a 4k form. Integrate that, that's the. So this is called the L polynomial of Hirzebruch. This is an explicitly written polynomial. L polynomial. It is not exactly a polynomial, but in each case it becomes a polynomial. It's some expression in terms of trigonometric functions. If I have it here, I'm not sure. Oh, I do have it actually, yes. This L is the following polynomial. I hope I didn't go out of line, did I? No, I'm within the border, I guess, still. Okay, so this L of M is equal to product of, so you just take the following polynomial, xi, over tangent hyperbolic I over I. This comes out to be equal to 1 plus 1/3 of P1 plus 1 over 45. Times 7p2 minus p1 squared plus the next term is just there's even bigger fraction here, and then we will deal with this. So this is the L polynomial. As I said, it's a kind of hyperbolic tangent function. It's an explicit expression, and you replace xi's by term roots of the manifold, and then you get these expressions in terms of comparing classes. Okay, so this is, or this was before Etienne the second example of an index theorem that already existed. And by the way, Etienne index theorem also gives you this result. Right hand side of the index now will produce this result. And there is a third example which is which existed. That is Riemann-Roch theorem. So the Riemann-Roch is applied to Dolbeau complex. Again, this was done by Hirzebruch in general for complex, for algebraic smooth projective varieties. Algebraic. It's a generalization of classical Riemann-Roch. So this was, again, another example that existed and Etienne could rely on as a check that they have got the right result. So there were at least 3 big results before Etienne that can be interpreted as index theorems like this. But amazingly, the motivation for Etienne was not to kind of unify these 3 results. It was not this. There was another question that was, according to them themselves, that was the motivating question for the whole thing. And the question was why the A hat genus of spin manifolds is divisible by 16. It's always divisible by 16. So that was, I believe that was the original question, if my memory doesn't fail. So, but very soon they realized that what these complexes also, these numbers also are index of some operators. Again, showing that these complexes are index of operators is not difficult. That's what we did more or less today, with some things still lacking. But to prove the general result and to derive these are special cases was the big thing. So I think we are good for now to stop. So I'm going to stop the video, and then you can ask your questions if you want. Or maybe you have questions already. Any questions or comments? Okay, so let's see how video today will look like.